All right, it is 10. So we will get started here. Let me get the PowerPoint up. All right, so what we ended on Wednesday is that we were talking about this idea of energy transfer, thermal energy transfer. And we were looking at the equation where heat, this Q, equals mass of our object, the specific heat capacity of our object, multiplied by the change of temperature of our object. And just as a reminder, every time you see delta in this class, it means difference, um, delta for difference, and it's always going to be final minus initial, right? So final temperature minus initial temperature. And we use this equation, Q equals mc delta T, to see how thermal energy can be moved between two different objects. So if I have two objects in contact, like metal and water, and they are at different temperatures, I can figure out a bunch of things, like the mass of a metal, mass of water, heat capacities, the change in temperatures, by using this relationship of any heat that is lost or gained from the metal has to come from water if it's a enclosed system. So that was the last problem we worked on Wednesday. The next thing we're going to talk about is pressure volume work. So we were talking about temperature heat work on Wednesday. Now we're going to talk about pressure volume work. And pressure volume work is when you have a volume change against an external pressure. So the easiest example of this is a piston in a car. When you push a piston up, you're pushing against the atmosphere. And so work is being done. Conversely, when the piston compresses again, work is also being done. So the equation for this is relatively simple. Work equals negative pressure, so the external pressure, multiplied by our change in volume. Now, the one tricky thing about this is when you do this equation, you want your pressure in atmospheres and you want your volume in liters. So pressure is in atmospheres and volumes in liters. And the reason for that is we need to have work in a unit of energy. Our unit of energy here is joules. So when we have a unit of atmosphere times liters, which we do when we do this equation, we can convert that into an energy by saying 101.3 joules equals 1 atmosphere liter. So that's why we want pressure in atmospheres and volumes in liters. So what we're going to start with today is just calculating pressure volume work. So I have a piston, and this piston absorbs 565 joules of heat, and it expands from 0.1 liters to 0.85 liters against an external pressure of 1 atmosphere. What was the change in internal energy in joules of the air within the piston? And was this overall an endothermic or exothermic process? So that is where we are going to start. So I'll give people a couple minutes to try and work through that. If you have questions while doing this, please let me know. Basically, what is delta E? That's what I'm asking in this question. So if you're not sure exactly what is exactly what we're doing here is that we want to calculate work first. So let's calculate work of the piston, because we have two things we need to calculate, right? We need to calculate work and we need to calculate heat. Remember, Q is heat, W is work. So to do work, it's W equals minus pressure. Well, pressure is 1 atmosphere multiplied by the change of volume. Like I said at the beginning, every time you see delta, it's final minus initial. So final is 0.85 liters minus 0.10 liters. And so your work is negative 0.75 atmospheres liters. Okay, but an atmosphere liter is not a unit we can really use when talking about energy. We have to be in joules. So I'm going to convert my atmosphere liters into joules. So our conversion is 1 atmosphere liter is 101.3 joules. And doing that conversion, it is negative 75.975 joules. Okay, so that's what our energy is in work. And Q was given. You just have to figure out, is Q positive or Q negative, right? So if I'm absorbing heat, that means I'm taking heat inside of me, which means heat is a positive number. If it said like heat left, then heat would be negative number. Here we have a positive number, right? So delta E equals 565 minus 75.975, right? So this overall change in energy equals 489 joules, right? So this is a positive number. If it's positive, that means I gained energy. And if I'm gaining energy, it's going inside me. So this is an endo process, right? If it's negative, that means it's leaving, and that would be exo. 76.01, yeah, close enough. That's only different than 0.04. So yeah, not going to make any difference. So yeah, remember, if energy is leaving, it's exo, that means it's negative. If it's going in, it's endo, and that's positive. All right, any questions about that, how we did it, any of the terminology? Anyone get lost in that explanation? The minus pressure, that's just part of the calculation. The minus P, that's the final volume always. Well, so what I did first, not quite sure what you're asking, but for work, right? It's minus pressure chain multiplied by delta V, which is always final minus initial, or delta V. So that's why it's 0.85 minus 0.1, and that's why the volume when you do is actually the change in volume is 0.75. Yep. All right. So we do have one more question on this, but I'm going to skip it for now because this question is actually a little out of place when I was looking over my notes this morning. And I had to re-upload the next PowerPoint. So if you downloaded the next PowerPoint like yesterday, it's going to be missing a few questions. So yeah, just if you don't have it up, if you didn't open it up within the last hour, just reopen it up because it's going to be a little different. But I share it anyways, so it should be updated. By the way, today is October 23rd. Happy Mole Day, everyone. Remember, Avogadro's number is 6.02 times 10 to the 23rd. October 23rd is Mole Day. So that's when all the chemistry people can be super nerds and be like, hey, look, October 23rd, Mole Day. So yeah, if you see anything like Mole Day on social media, if you see any moles like posted, that's why. I think the chemistry club is doing something for that too. I forget exactly what it is. I know they had like a scavenger hunt yesterday, I believe. Anyways, happy Mole Day. What we're going to talk about now is calorimetry. If you've ever looked at the back of like a candy bar or basically any food, and you've wondered, how do they know how many calories are in this food? One of the ways you could do that is called calorimetry. And what I'm showing you right here on the right is called a bomb calorimeter. What a bomb calorimeter is that you take whatever you want to measure the energy of, that would be your sample, and you make it into a little pellet, right? So you take your sample and you make it into a pellet. You then blow it up. You literally blow it up. That's why it's called a bomb calorimeter. You blow it up, and when you blow it up, this chamber is surrounded by water, right? And so you blow it up and you measure the change in temperature of water. So you measure the water change, right? And if you know the specific heat capacity of your calorimeter, which you should, you can calculate how much energy change, or rather, the change in temperature of the water, how much is that due to what I blew up? And our equations for that is that the heat change of the calorimeter is equal to the specific heat capacity of the calorimeter multiplied by my change in temperature of the water. So I'm measuring the change in temperature of the water. Once I calculate how much heat my calorimeter absorbed, that's what qcal is. How much heat did my calorimeter absorb? Then I can say, well, any heat that my calorimeter absorbed must have come from my reaction, because I'm blowing this up, right? I'm releasing energy. So any energy absorbed by my water has to come from my sample. So I can calculate, okay, how much energy was in my system? It's all based on the heat release, because if you remember on our last slide, energy is based on two things, heat plus work. Work is defined as pressure change in volume. Well, if I keep my volume constant, my change in volume is zero, because it's a constant value. If my change in volume is zero, I don't do any work, so I can measure the change in energy of a system solely based on how much heat's released. So if you have like a Snickers bar, right, what you can do is you can go and blow up that Snickers bar, measure the change in temperature of the water, and use that to calculate how much energy was in that Snickers bar. Now you can figure out, if I have like eat like 10 Snickers bar, how much energy is that? Yeah, coffee cup calorimetry. is something we normally do in Gen Chem lab. I don't know if we're going to do it. I don't know if you guys do it this semester because of time restraints. But yeah, that's actually going to be one of my next slides that I talk about. All right. So I do have a question. I just want to see if I want to do this one or not. So so these are quite complicated. So I'm going to do question 1 and then question 2, and question 3 is one you can try on your own. But there's a lot of moving parts to this, a lot to understand. So I'm going to take care of question 1 and 2 for us. All right. So mothballs smell horrible. They are mainly made of naphthalene, a hydrocarbon. Let's say I take 1.025 grams of naphthalene and I blow it up in a bomb, right? So I blow this up in a bomb and my temperature changes. So mass of naphthalene. Let me be thorough and like write down like my variables when I come to them as a way to show you how to solve these questions. So mass of naphthalene is that my molecular weight is given as well, right? So temperature, initially, my temperature initial is 24.25 centigrade. My temperature final is 32.33. What is delta E of reaction? So what is delta E reaction or system? When I say reaction, that also means system. So what is that? In units of kilojoules per mole, because I wanted to solve in kilojoules per mole. And the heat capacity, remember CS or C equals heat capacity of the bomb is 5.11 kilojoules per change in Celsius. All right, so those are all of our important variables that I just pulled out, right? And I already saw, what do I need to solve for? Well, I need to solve for delta E reaction or delta E system, which is given in this equation, right? So I need to solve for this. To get delta E system, I need delta Q reaction. So I need to solve for delta Q reaction. To solve for delta Q reaction, I need to solve for delta Q calorimeter, because any heat from the calorimeter must have come from my reaction. To solve for delta Q calorimeter, I have this equation where it's the heat capacitor of the calorimeter multiplied by the change in temperature. Before I get down to actual number crunching, did anyone get lost on that logic? What I said, does that make sense of how we go from reading this question, pulling out the important information, finding what we need, like our unknown variable that we need to get, and then trying to look at our equations and find a path to solve that? Did anyone get lost on that or want a another explanation, more detailed explanation? So I can explain it one more time. Sure. All right. So I pulled out all my variables. I'm blowing up a mothball that's 1.025 grams. And I want to know, when I blow up this mothball, how much energy was released with the units kilojoules per mole. Okay. So when I blow it up, my calorimeter changes temperature. So that's the information that I know. Okay. So to find out how much energy is in the system, I have to know how much heat was released when I blew up my mothball. That's this equation, the one I just put a number 1 next to, right? To know how much heat is released by blowing up the mothball, I have to know how much heat was absorbed by the calorimeter. That's equation number 2. To figure out how much heat was absorbed by the calorimeter, we have this equation where the heat absorbed by the calorimeter equals heat capacity of the calorimeter multiplied by delta T. That is our logic here. Delta is always different. Here we don't have a delta Q. We have a delta T for change in temperature and delta E, which is saying what is happening to our system when we blow it up. How much energy is being released upon explosion. So we have a change in temperature and a change of energy, and we want to calculate change of energy. So it's not quite change in heat. Those are two subtly different things. Heat is like energy, temperature is a measure of the energy. All right, so the first thing we want to calculate is QCal. That equals CS, which is 5.11 kilojoules per Celsius, multiplied by delta T. Final minus initial, 32.33 minus 24.25. So the heat absorbed by our calorimeter was what, 41.3 kilojoules. So that is how much heat was absorbed by our calorimeter. Q is not change in heat. Q is just heat. Delta Q is change in heat. Q is just a measure of heat. That's just a number, right? Delta, you're looking at a difference. Q is just a number. And we don't have any delta Qs here. We're just looking at Q. All right. So we know how much heat was absorbed by the calorimeter was 41.3 kilojoules. Now I know how much energy was released by my reaction because we're assuming that any heat absorbed by the calorimeter came from my reaction. So I can rearrange this equation, say Q reaction equals negative Q cal. I'm just switching the negative sign, right? So my Q reaction then equals negative 41.3 kilojoules. And my Q reaction and my delta E system are actually the same thing. Okay. So we got just the plain energy. Questions about that logic? We're not quite done, but questions about that. And I say we're not quite done because I want kilojoules per mole. And right now I'm just in kilojoules, right? So the way to go about this now is you have to realize you blew up a small sample of naphthalene. I want to figure out how many moles of naphthalene did I blow up? That's why I gave you the molecular mass. So I have 1.025 grams of naphthalene that I blew up. There are 128.17 grams for every 1 mole of naphthalene, right? So what I need to do is I divide those two numbers, and I actually did not do that on my answer key, so I'm going to do that really quick. Oops, I don't know how to spell calculator. So 1.02 divided by 128.17. So I have 7.958 times 10 to the 10 to the minus 3 moles. That's how much naphthalene I had. So to get kilojoules per mole, you take Q reaction divided by how many moles you blew up. So it'd be negative 41.3 divided by 0.007958. And it is 5.19 times 10 to the 3 negative kilojoules per mole. Delta E for blowing something up should always be negative, right? Because you're releasing energy. And the way that I remember that is think about a bomb. If I drop a bomb somewhere, am I taking in energy or am I releasing energy? And you release a lot of energy. So your energy better be negative when you blow something up. If you get a positive energy, you did something wrong. Yeah, so delta E should always be negative when you're exploding things, because that's what we just did. We blew up something and we measured the change in energy. All right. Questions about that lovely bomb calorimetry problem? How to figure out heat change in a material. All you need to do is explode. Can you get more examples? Maybe. Let's see what we have on the next slide. Hey, look, we have more examples. But this time, we are talking about delta H. So just to take this one step further, we can calculate the change in enthalpy of a system using calorimetry. So in our last example was bomb calorimetry. Here we're doing coffee cup calorimetry, where it's the same idea as a bomb calorimeter, but instead of blowing stuff up, you are mixing stuff. But it's the same idea, same logic, where I mix something in water, I measure the change in temperature of the water. My pressure, my volume doesn't change, my pressure doesn't change. And so any change in temperature that I measure must be due to the mixing. And we looked at this on Wednesday too, where we looked at energy transfer. Remember, energy transfer or heat equals mass times CS times delta T. So if my solution changes energy or changes temperature, all of that energy must have come from whatever reaction I'm doing. In the example I was saying, you're dissolving something, you could have a chemical reaction as well, where you do a chemical reaction and you measure the change in temperature of the solution, and you will see, okay, how much energy was released or how much energy was absorbed. And here, delta H, H means enthalpy. I could give a whole lecture, whole 2 lectures probably, on what delta H actually means for us. When you see enthalpy, think of heat. That's a good enough approximation of what enthalpy means. So the change in heat of a reaction when we don't have any other work going on is simply Q. So if I'm doing any reactions and I want to know what the change of enthalpy is, the change of heat during that reaction, I can use calorimetry. And it's the same idea as the bomb, except here we're not blowing up. We're just doing any other type of reaction. So I have 2 examples for this. I will do number 2. I'll do the next example again to show you how to do calorimetry again, because these are very complex. And then I'll let you do number 3, right? All right. So instant cold ice packs. How instant cold ice packs work is that you have 2 containers, or you have a container rather separating 2 chambers. In one chamber, you have ammonium nitrate. In the other chamber, you have water. And to activate these cold packs, you have to break the divider. So you kind of like snap the cold pack, and you will hear that like little break, and then it'll start to feel cold. The reason why it starts to feel cold is that you're taking a solid and you're dissolving it in water, which is an endothermic process. So when you put it on your skin, right, the chemical reaction will take heat from your skin, which we feel as cold. So I want to know, when we dissolve ammonium nitrate, what is my enthalpy change? Okay, so what is enthalpy? So when you see enthalpy, always think of H. So what is enthalpy change for this reaction in kilojoules per mole? And it's actually given later. Calculate the change in enthalpy for the reaction in kilojoules per mole. All right. So we have some equations. So my delta H equals the heat of the reaction, because we're at constant pressure. Unless you are doing some weird chemistry, you're always going to be at constant pressure. Your pressure doesn't change inside of a lab. So we're at constant pressure. So it's Q reaction. At Q reaction, this is our next equation. I don't know why I'm rewriting it, but Q reaction equals minus Q solution. And so if we're doing a calorimetry experiment, that's what I'm measuring. I'm measuring the solution. So negative Q solution equals negative mass of the solution multiplied by the CS of the solution multiplied by delta T. All right. So to solve for delta H, I need delta Q reaction. To solve for delta Q reaction, I need mass of a solution, the heat capacity of a solution, and the change in temperature of a solution. So let's see if I'm given those. All right. So I have 1.25 grams of NH4NO3. So my NH4NO3 is 1.25 grams. And it's dissolved in water to make a volume of 25.0 milliliters, right? Temperature initial, okay, I need this. So my temperature initial is 25.8 centigrade. My temperature final is 21.9. So I just got the information for delta T because I have final minus initial, right? T final minus T initial. So that's good. That's good. Calculate the change. Use 1.02 grams per mil as the density. So density of this equals 1.02 grams per mil. And the specific heat capacity is 4.184. All right. So just mining the problem, that's what I have so far. I can more or less just ignore all of this now. I don't want to do that in case you want to read it, but I can ignore it because I wrote down the important stuff on the right there. Before I move on, any questions so far? Again, I know these are complicated, so that's why I'm working these out, and then I'll let you go wild on the next one. All right, so the only thing we're missing is mass of solution. I'm sure you're very tempted to use 1.25 grams as your mass. I'm sure many of you out there are like, I have a mass, I'm going to use it. These are the times when you need to slow down and read what the equation says, right? The equation says I need mass of solution. That 1.25 is mass of a solid. A solid does not make a solution, right? Your solution is the solid plus water. Because remember, we talked about what a solution is back in the liquids chapter. So my solution has a volume of 25 milliliters. The density is 1 milliliter, 1.02 grams. So when given a volume of solution, to get a weight, you need the density. So that's where the mass of the solution is coming from. That part is very, very easy to get wrong, to get tripped up on. So my mass of solution is 25.5 grams. Now I have everything I need to calculate Q reaction. So Q reaction mass is always negative. It's not the mass is negative. Like you can't have a negative mass. That doesn't make sense. What is negative is the heat of the solution, because what we're really solving for is Q reaction. That's what we're solving for. And Q reaction equals negative Q solution because it's a closed system. Any heat change in my solution must come from the reaction that I'm doing. So that's where the negative sign's coming in. They're equal but opposite processes. And to solve for Q solution, I have Q equals mass CS delta T, which we used on Wednesday. So that's why it says like negative mass in the equation. But it's not that the mass is negative. I could put that negative sign anywhere. It's just what the we're solving for Q solution. Yes, density equals mass divided by volume. That is correct. All right, so let's solve for Q reaction. We have all our pieces there. So Q reaction equals 25.5 times 4.185 multiplied by final minus initial, 21.9 minus 25.8. So that should be what? Negative 416.1 joules. How do I know it's joules? Because the CS tells me it's joules. 4.184 joules per gram centigrade. So that's my Q reaction. And all I did was multiply mass times CS times delta T. So I'm actually going to move that down. So remember, I want to solve for this in kilojoules per mole. So my Q reaction is negative 0.416 kilojoules. I just converted the joules to kilojoules. You just divide by 1,000. So like our previous problem with naphthalene, I want to know how many moles. I want to know this in kilojoules per mole. So I want to know the heat that we just measured. How many moles of ammonium nitrate caused that change? So if I have 1.25 grams of ammonium nitrate and I have 80.043 grams for every 1 mole, the amount of moles of ammonium nitrate I used to create this heat change was only 0.0156 moles, right? So to get to kilojoules per mole, I take how many kilojoules that heat change was. I divide that by how many moles I used to make that change to get my final answer of negative 26.7 kilojoules per mole. So like I said, why is the mass negative? Mass isn't negative, right? You can't have a negative mass. The negative sign is because we're calculating Q reaction. Q reaction we get from negative Q solution. So the negative sign is coming from our first equation. I could put the negative sign anywhere. It doesn't matter. All I'm saying is I'm solving for Q reaction. That's negative Q solution. So Q solution is mass times CS times delta T. Therefore, negative Q solution is negative multiplied by mass CS delta T. Yeah. Delta T is change of temperature, right? So delta always means change. Whatever it's in front of is what we're changing. So delta T is change in temperature. So that 80.043 is, yeah, that's how we find number of moles. So 1.25 divided by 80.043. Okay. I know there are a lot of moving parts to calorimetry questions. There's like, this is just one question and you're doing like 5 calculations. Very involved. That's why we're doing many examples. So instead of me just repeating what I just said already, now's the time for you to get on that bike and try to ride it. Don't worry, daddy or mommy is going to be right behind you. In case you start to fall, they're going to be there to hold you steady. But training wheels are taking off now. It's time for you to ride. I have zinc, and I put that in hydrochloric acid. If I had 0.103 grams of zinc, and I combine that with hydrochloric acid to make 50 milliliters of solution, and all my zinc reacts, my temperature is changed from 22.5 to 23.7. What is delta H in kilojoules per mole? Was this exothermic or endothermic? All right, let's ride that bike. Give me a delta H. If you have questions, let me know. But yeah, we're going to use the rest of the time today to see if we can solve this. Hopefully at this point you have at least defined your variables. So I'm going to at least do that for us. Okay, so like our previous question, we want delta H reaction. I want this. To get delta H, I need Q. To get Q reaction, I need Q solution. CS, easy, given. Delta T, again, easy, given. Final minus initial. Mass of solution, again, don't just put the zinc mass. That's not a solution. Solution is zinc plus hydrochloric acid. So we have 50 milliliters of solution. Our density is 1 mil per 1.03 grams. So the mass of our solution is 51.5 grams. Remember to put your answer in kilojoules per mole, not just joules. I want kilojoules per mole. All right, so let's solve for Q reaction, right? Dissolving this zinc, how much heat was absorbed or released? So Q reaction equals negative mass is 51.5 multiplied by 4.184 multiplied by my change in temperature. 23.7 minus 22.5. And so my change in reaction was negative 258.6 joules or negative 0.2586 kilojoules. Because that's what I ultimately want. I want kilojoules per mole. So that's how much kilojoule was released, how much energy. Now to get kilojoules per mole, I have to figure out that energy change was caused by how many moles of zinc. Well, zinc, there's 0.103 grams of zinc in my reaction. Looking up my periodic table, the molecular weight of zinc is 65.38 grams for every 1 mole, which is 1.58 times 10 to the minus 3 moles. So to get kilojoules per mole, I divide the two. Which is negative 164.1 kilojoules per mole. So that is our answer for that problem. I'm teaching right now. So if we now are looking, sorry, I had to deal with the dog. So if we're looking at whether this is exothermic or endothermic, again, we look at the sign. We are releasing heat, right? Our heat is negative. Our change in heat was negative. So we lost heat, which means we release heat. That's exothermic. Any questions about this problem? Yeah, so usually in these problems, what I will give you like a volume and a density, and that's how you get massive solution. I might also just give you massive solution and mass of a solid, and you have to figure out which one you have to use. Again, when you're doing Q solution, always do mass solution. And if you want even more practice, which I do suggest you do, you will see a problem like this on your homework. So that will be even more practice. But that is calorimetry. Now I know there's on this PowerPoint, there's like 6 more questions. That's fine because one of my PowerPoints, I think on Friday only has 2 questions. So it is laid out completely fine. But any last questions before I let you go for the weekend? If not, as always, same old spiel, put this online, homework on Sunday. Have questions, want to meet with me, shoot me an email. Otherwise, have a good weekend and take care, everybody.